Welcome back. Last time we were talking about taking a curve and reparameterizing it so that instead of distance, instead of the parameter t representing the time when you visit a location on the curve, we could represent it by the distance traveled along the curve. But if you think about it, the curve really has many different ways that you could travel along it. You could decide to go at a very slow pace and then fast, or you could decide to go at a really fast speed, stop, go back, go along. In all these different ways, you're visiting the same points on the curve, but you're doing it in a completely different way. So um, the thing is, the curve is just the curve. It's not like we have, it's not like we are, there's something special about traveling along it in any way. Instead, what we would say is that, okay, this curve really has some intrinsic properties. There's something special about being at this point on the curve that doesn't depend on what the parameters are of your how you're tracing the curve. And so this portion of this lecture is about what would we say about what's happening at this point on the curve if we like whatever the parameterization is of the curve. So what we're going to see is that there's going to be three natural vectors that make up that occur at every point. They're going to be called the Frenet frame or the TNB frame, and there's some number associated to the point on the curve that says really how bendy or twisty the curve is. So no matter how you parameterize the curve, these concepts are intrinsic to the curve. So let's first talk about this Frenet frame, the TNB frame. Let me put them all down here so that I can just draw once the picture and talk about it. So we're talking about this curve, and this curve we're going to think of about being in 3 dimensions. Okay, and we're going to look at any point on this curve, and we're going to talk about, well, what about the direction that this point is moving in as it goes through, that the particle is moving as it goes through this point. And so we can talk about this tangent vector, the direction of the tangent vector, and whether you're going fast or whether you're going slow, this tangent vector is always pointing in the same direction. So because we want to normalize and make it so that the tangent vector is no matter how, the speed at which you go through the point, we keep track of just that direction, we're going to create this unit tangent vector. Which corresponds to taking this tangent vector and normalizing it by the length of it. So no matter what the speed is that you're going through the point, when you divide by the speed, you get just the direction of the tangent vector. So this is going to be our unit tangent vector. This is t of t. All right. Also here at this point, you can talk about how this vector is changing over time. So how is the unit tangent vector changing over time? So here, right, this is the unit tangent vector, here the unit tangent vector, and at this point, now the unit tangent vector, let me actually use a different color for this. The unit tangent vector is now going to be turning in this normal direction. So this is going to be the unit normal vector. And what it corresponds to is the direction in which the curve starts turning. So what are you feeling as you're driving in this car? Your car starts turning. You're starting to feel your velocity vector is changing, and so this normal vector is talking about, well, how is this velocity vector changing? And so when you have, so even if we were in 2 dimensions, we could draw this tangent vector and this normal vector. When we're in 3 dimensions, we can draw one more vector, which is called the binormal vector, and it completes the 3-dimensional basis. So we can take the unit tangent vector, we can take the normal vector, right, and this Tn, and then we need to do the 3rd dimension. The cross product of these 2 vectors is called the binormal vector. Right, this is our B vector. And so at all points on this curve, let me see if how my hand looks here. At all points on this curve, you've got this vector that's following along, these 3 vectors that are slowly changing and that are following along this curve. Go along this curve, and so let me pull up another picture here that we can use to see this a little bit more in action. And I've put a link to this on our web page. So this is one of the many demonstrations that is available at the Wolfram Demonstration Project, which basically lets you see really cool things that Mathematica can do. Here's an example of a curve, right? This is our helix that we're used to drawing, and what has been created here, which does it say who this, by Nick Bykoff. Nick created a visualization of what's happening. So here you can see the green vector here is the tangent vector. And as we go along the curve, this green vector shows the direction that our particle is moving at that time. All right. So next is that unit normal vector. Maybe I'll turn it this way, and maybe we can make this a little bit bigger so we can see. So the green vector here you can see is, let me make the tube a tiny bit smaller. The green vector is always pointing in the direction that the curve is going. So as this curve turns, then the orange vector says, how is that unit vector changing? How is the tangent vector changing? And we can see that it's kind of pulling, like this green vector starts out pointing towards us and then ends up pointing up in that direction. And so what that means is that the rate of change of that is kind of pointing inward towards the center of the helix. So that's the green vector and the orange vector. And then the purple vector corresponds to the cross product of those two. If you take the green vector cross the orange vector, you get the purple vector. All right. So that's how you can calculate these. So in order to calculate those, you calculate r primed of t divided by the length of r primed of t. You calculate t primed of t, the derivative of the tangent vector, unit tangent vector divided by the length of the unit tangent vector of that same quantity, and then the binormal vector is going to be one more vector of length 1, which is calculated using the cross product. So those are 3 vectors that are associated to every curve in space. And the last thing that this one other idea that is related to, that's always available at every point on a parametric curve, is the curvature of that point. And what the curvature does is it's telling us how fast t, this tangent vector, is changing with respect to the distance traveled. Okay, so this is a bit weird, right? Up here we were calculating t primed of t, but here now we want to take so this is t prime to t, which is the derivative with respect to t of t. And now what we want to calculate is the derivative with respect to s of t. And if you think about it, what's happening as you go along your curve, we want to know, does it curve really fast or does it curve slowly? And remember, we'd like this decision to be something that doesn't depend on time. We'd like it to be something that depends on space. So here we would say this, at this point, I'm gearing up for the next thing that I want to say. At this point, this curve is not very curvy. Not very curvy. And at this point, the curve is very curvy. Very curvy. So there's a formula for it. I'll get to that in a second. But the key point that I want to say is that what's another way to talk about how curvy a curve is? It would have to do with how big of a circle would nest in this space. So if a function is really, really curvy, so like up here, the circle that nests along there is a really small circle. But if you're not very curvy at all, then the circle that nests in the curve is going to be very big. So if you want a geometric understanding of what the curvature is, it corresponds to the size of the circle that lies on the curve. And because this has an inverse relationship with the actual how curvy the function is, we would expect this type of inverse relationship. So in fact, if you figured out exactly the radius of that circle that nests, and you take 1 divided by that, you get the curvature. So how do we calculate the curvature? We calculate the curvature by taking the derivative of t with respect to s, but t is a function of t and not of s. So we have to use the chain rule. And so you get something that looks like this. The derivative of t primed of t divided by r primed of t. Now, I'm going to say something on the side here. This is actually rather ugly to calculate. T is a function that it's a derivative divided by the length of that derivative. So this is just a polynomial in t. This is a vector. So what that means is that this t of t is really a bunch of rational functions. And so its derivative is annoying. So the easier way to calculate the curvature is this function, where you take the derivative of r, the second derivative of r, you take their cross product, and then you divide by the length. You take the length of that, and you divide by the length of r primed cubed. You can check the book if you want to see the details. All right, so let's do an example. Find the vectors of the Frenet frame and the curvature of this curve. Okay, so this is that same picture that we just saw in Mathematica. We're looking for the vectors of the Frenet frame and the curvature of this curve. So for the Frenet frame, we're going to need to calculate t of t. So you do that by taking the derivative and finding the length of that derivative. Right, so what do we get? We get that minus sine of t comma cosine t comma 1. That gives us the length of it is going to be equal to sine squared t plus cosine squared t plus 1, which we said was equal to the square root of 2. So in this case, it's not a polynomial in t, or a more complicated function of t, luckily. So that's going to make calculating the derivative of t easier. So when we take r primed of t, divide by the length of that, we get this as our unit tangent vector. All right, next. When we want to calculate the normal vector, we need to take the length of the derivative. We have to take the derivative of the unit tangent vector and its length. So in this case, the derivative of minus sine of t over root 2 is minus cosine of t over square root of 2. The derivative of cosine of t over root 2 is equal to negative sine of t divided by root 2, and the derivative of a constant is always 0. So the length of this vector is going to be square root of negative cosine of t over root 2 squared plus negative sine of t over root 2 squared plus 0. We can factor out the 1 over root 2 times square root of cosine squared t plus sine squared t, which is the square root of 1. So this length of the derivative of the unit tangent vector is 1 over root 2. And now we have to take our unit tangent vector, divide by that, and that's going to cancel out the 1 over root 2 that's in each of them. So we get negative cosine of t, negative sine of t, comma 0. So these two vectors, the tangent vector and the normal vector, the unit tangent vector, the unit normal vector, are here. The binormal vector, you calculate using the cross product. So you have to take, so we have a 1 over root 2 we factor out, and then we do negative sine of t cosine t 1, negative cosine t negative sine of t 0, and I thought I had that here, but we're happy to do it. So we have ij negative sine t cosine t negative cosine t negative sine of t. Then we go down, 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 minus up, up, up. And so what is I? The first thing I is cosine of t times 0. So that's 0i. In terms of j, we get plus 1 times negative cosine of t j. K gives us sine squared of t times k. And then the other direction, we have negative times negative cosine squared of t k. We have what in terms of I? We have minus negative sine of t I, and we have 0 j. And so the binormal vector, we have sine of t I, we have cosine of t, negative cosine of t j, and we have sine squared of t plus cosine squared of tk, which is just 1k. And so this is our binormal vector. All right, last thing, we need to calculate the curvature. So to calculate the curvature, we've already calculated the t primed of t. We already calculated r primed of t, so we can use this formula here for the curvature. So in this case, we had 1 over root 2 divided by root 2, which is 1 over 2. So if the curvature is 1/2, we're seeing that the curvature is a constant. And so would we expect that the curvature is a constant? And let's to check that out, let's go back and think about our curve. And if you think about this curve looks the same no matter where you are on the curve. So we would expect that a circle of the same radius would nest the same way the whole way along. So it does make sense that kappa is a constant. And what kappa is a constant is saying it's saying that there would be a circle of radius 2, because 1 divided by 1/2 is 2, you'd be able to nest a circle of radius 2 in the Frenet, in our curve. That would be a fun thing to explore. Alright, so let's stop here. One more short video about these concepts of vector functions. See you shortly.